Hello, everyone, and welcome to today's webinar. We are thrilled that you could join us for this three-part series titled Cryo-EM Back to Basics. So for today's session, we're going to be focusing on cryo-EM sample preparation and imaging. If you're able to join us next month, we will walk you through data processing and interpretation. And then in March, we'll be focusing on some of the common limitations in cryo-EM and how to overcome them. So before we begin, I just have a couple of quick housekeeping notes. So the webinar will run for 30 minutes, followed by a 15-minute Q&A session. And you'll notice that throughout the webinar, you'll be able to submit your questions in the Q&A box in your toolbar. You can also vote for the questions that you're most excited about. And for any questions that we do not get to today, we will follow up with you next week. We will also be sending everyone at this webinar a recording, and that will also be sent out next week. So now it is my pleasure to introduce our speaker, the CSO of Nanoimaging Services, Giovanna Scapin. So Giovanna has extensive industrial experience in the field of structural biology and structure-based drug design from her time at Merck. She trained at the New York Structural Biology Center in order to learn cryo-EM, and then she played a pivotal role in establishing Merck's cryo-EM facility. Since joining NIS in 2020, she has been instrumental in advancing cutting-edge research in this field. So, without further ado, please join me in welcoming Giovanna Scapin. So, Giovanna, over to you.
Hello, everybody, and welcome to this three-part webinar on fundamentals of cryo-EM. This is not meant to or supposed to replace more in-depth seminars and videos on cryo-EM that are available on the web, and that we are inviting you to check out if you really want to learn more details about theory and practices in cryo-EM. What we intend to do is to provide you with some very basic knowledge of the technology, of the infrastructures needed to set up a cryo-EM lab, and of the vocabulary we use when we talk about cryo-EM experiments. In the first of these three webinars, I will address sample prep and imaging. And here already there is something that means something different when talking to different people. In microscopy, sample prep is not how we get the biological sample, but how we prep it to be visualized using the microscope. And so in cryo-EM jargon, sample prep actually means specimen prep. And this is what I will be describing in the talk. This is a brief overview of what I'll cover, basic information about the instruments, the tools, and the infrastructures we need, what advancement in technology allowed for the big jump in resolution about a decade ago, how we prep grids, and how we collect data. I will not talk about how we get the biological samples and what characteristics they should have. We will be focusing on learning the technical specs and requirements of electron microscopy. And that will make much more clear why some of the challenges we experience in cryo-EM are related to or depend on the biological sample we have in hand. In the third webinar in the series, we will discuss some of these limitations and present some of the solutions we might have. The most important piece of instrumentation we need is, of course, an electron microscope. In a general sense, the anatomy of an electron microscope is very similar to that of a regular light microscope, with a light source, a specimen holder, and a detecting device, but with some fundamental differences in how we generate the beam and how we detect the signal. In transmission electron microscopy, the beam is generated by an electron gun, and it's then transmitted through an ultra-thin specimen. After passing through the specimen, the scattered electrons are then focused by electromagnetic lenses onto an imaging device. The voltage at which the electrons are generated, for example, 200 or 300 kiloelectron volt for the most common microscopes, define their energy, the electron energy, and their wavelength, ultimately influencing the details that we can see and the resolution that we can obtain. There are other differences between the smaller and bigger microscopes. One of them is the lens systems, which is much more complex in the higher end cryos than in the smaller glaciers. which allows for a more parallel and intense beam. Electron microscopy is not a novel science. The first electron microscopes were built in the 20s and 30s and were used mostly for material science because the biological matter would be destroyed by the high energy beam. Vitrification, as we know it, was introduced in the 80s as a system to preserve and partially protect the biological specimen from the incoming electrons. And after its introduction, we could actually finally image this biological material. The way we vitrify the sample nowadays is not very different from how it was done 50 years ago. It might be more automated, but the principles remain the same. Vitrification allowed for the visualization of the first biological blobs, and then the resolution got progressively better, although the technique was somewhat limited to massive things with lots and lots of symmetry. But then in 2012, 2013, rapid advances in the field resulted in what we know now as the resolution revolution. And Cryo-EM started to become competitive with X-ray crystallography in obtaining atomic structure for many different systems. The resolution revolution was propelled by rapid advancements in how images produced by an electron microscope were captured and analyzed. The first one was the evolution of the physical cameras used. Early on, images were collected on a film, a process that was very slow, very laborious, and with very limited resolution. The introduction of CCD cameras was one major step forward. But these cameras use a scintillator to convert the electrons to a light image, and then a fiber optic faceplate to transfer the image to a CCD or more recently to a CMOS image sensor for analog recording. This process makes the cameras relatively slow. And in addition, when the results are converted and recorded, there is a loss of high resolution details. The introduction of the direct electron detection cameras was the big revolution. These cameras allow to directly measure the electron images, thus avoiding the loss of details derived from the conversion steps. They are very sensitive to recording low-dose electron images because they have an excellent detective quantum efficiency, or QE. And they're also much faster than older cameras, thus allowing another important change in the way the images are recorded. Films and CCD cameras record still images. In order to get high resolution information, we need to work with the highest possible total dose, usually over a long exposure time. But these two factors cause the particles in the sample to move. A still recording of a moving object results in a blurry image with loss of resolution. But introduction of the high-speed cameras allowed for a different type of recording, not a still image anymore, but a movie with up to 50 frames that could then be internally aligned, resulting in a much clearer and more detailed image. This is the process we refer to as movie alignment, and as we will see in the next webinar, is the first step on any data processing. So we have microscopes and cameras. How do we prepare the specimen? We always say we make grids, but what are these grids? Grids are basically support objects with a relatively simple general anatomy, but many possible variations. The grid support is a 3 millimeter in diameter flat circle with a mesh. They can be made of copper, gold, or other possible materials. The mesh is usually a square mesh, and the size, 200, 300, 400, refers to the number of squares per linear inch. A higher mesh number means more squares per inch, which result in a finer grid. Recently, a completely different type of grid, the so-called hexafoil, have been reported. In this case, the mesh is hexagonal, making for an even finer kind of grid. On top of a mesh, there is a thin, usually a few micron thick foil, made generally of carbon or other material, gold or other material. This foil can be continuous or wholly. in which case there are regular spaced holes carved into the material itself. During vitrification, the sample gets trapped in the holes and suspended in a thin layer of ice. The number reported near the grid type, in this case, refer to the hole size and the hole spaces, 1.2, 1.3, 0.6.1, etc. There is a somewhat special type of hole grid, which are called lacy grids, in which the holes are not regular at all, and the amount of visible support carbon varies greatly. Different samples react differently with all the different grids. And so the choice of what grid to use is very arbitrary at the beginning, but then it becomes more and more informed as we proceed with the experiment. There could be a final component on the top of the foil, which we refer to as a support film. This layer is usually added by hand manually, and it's used to address specific uses like, for example, low sample concentration, the presence of preferred orientation, or the fact that some samples prefer to stick to the carbon rather than move into the ice. Because of the materials they are composed of, grids are very hydrophobic, but the samples we want to put on the grids are usually very hydrophilic. And so in order to be able to use the grids, we need to increase the hydrophilicity. This is done by procedures that are known as glow discharge or the more complicated plasma clean. The procedure used and the parameters that are used during the process affect the resulting high thickness and particle behaviors, and thus are part of the variables that we analyze during a screening step. Now we have a box of grid ready to go and the protein sample at hand, and we need to freeze the protein sample onto the grids. How do we do this? The process actually is simple. About 3 microliters of sample are deposited on a grid, and then the excess liquid is removed by blotting. And after blotting, the grid is plunged into liquid ethane and frozen. This can be done manually, and we still do it manually in our laboratory sometimes. But nowadays, we mostly use semi-automatic instruments. The most well-known of all is the Vitrobat. The Vitrobat uses the same blotting procedure we just described. Other instruments, such as the Chameleon or the Vitrojet, use different approaches for sample deposition and thin. And different methods can have a remarkable effect on the resulting grades. Another variable that might affect the quality of the sample and the grid itself is the time to freeze. And two major considerations are always the speed at which this process is carried out and the reproducibility of the grids. Reproducibility especially is not great, which makes grid preparation still a very empirical step in the workflow, and that's why we need to do a lot of screening, as we will see in a few slides. One more thing that needs to be taken care of is that to avoid ice contamination. And for this reason, all of these above mentioned processes should be carried out in a humidity control room with a relative humidity of less than 20%. As I said before, the energy of the electron beam can be very detrimental to biological sample, hence the need to protect it when in the microscope. We already know that vitrification can be used for these purposes, but there is another procedure that is worth mentioning, and it's the negative stain. This involves layering a solution containing the biological sample of interest onto a grid, usually a continuous carbon grid, blotting away the excess solution, letting it dry, and then covering it with a heavy metal stain. Negative stain grids can then be visualized with the same microscopes we use for Cryo-EM. But since they are basically room temperature specimens, they can be analyzed with lower instruments like a T12 operating at room temperature. Why do we use negative staining? It's faster and cheaper at Cryo-EM. It has a higher contrast, so we can actually see smaller entities, but it does have a much lower resolution, which is dictated mostly by the size of the stain we use. It can introduce some artifacts, but it's a great way to assess, for example, the quality of a sample, monodisperse versus aggregate. As we can see in this picture, this sample is extremely well behaved, and we have a few individual particles on the image. It can also produce low resolution envelopes that sometimes are all we need to be able to dock known components into a complex, for example, or to visualize an overall shape of a sample. And it's a really great way to visualize samples' complexity and flexibility in many different cases. On the other hand, Cryo-EM is slower, more expensive. It has a much lower contrast, so the small objects are quite difficult to see. But it retains the almost native state of the samples, and it can really produce highly detailed images that we call at the end resolution maps of the sample itself, which are essential if we want to visualize atomic details of the sample. From secondary structural elements, for example, to positioning of side chains, to interactions made by a ligand with its receptor. Let's circle back to the vitrification process for a moment, because there are a couple of more steps that we need to do before imaging, especially if we are using one of the most modern instruments. So just to repeat, the sample happily tumbling around in solution is deposited on a grid, and then the grid is blotted before being flash frozen in liquid ethane. At this point, we need to handle the grid once more before getting into the microscope, because the grid needs to be clipped, which means we need to provide the very flimsy grid we just froze with a hard edge that can be used by autoloader microscopes to pick up the grid and position it on the stage. The other thing is that usually we prepare many more grids that we will end up using, and an organized grid storage system that allows the users to store, organize, and retrieve multiple grids at liquid natural temperature is a must in a Cryo-EM lab. Okay, now we have all the specimens ready to be imaged, and in order to image them, we need a fairly complex infrastructure, which is composed of course, microscopes, ideally one lower-end microscope, 200 or less, for screening, and one higher-end microscope, 300 kilo-electron volt, for high-resolution data collection. If we do a lot of room temperature negative staining, it might be worth having a smaller microscope, 80 kilo-electron volt, for example, side entry, room temperature scope, simpler to use and to maintain. We need cameras. Fast direct electron detectors, such as the Gatan K3 or the Falcon 4 from TFS, are a must for the higher-end microscope. For room temperature negative staining microscopes, integrating CMOS detectors can be more than enough. We need computers in order to control the microscopes, and data collection software in order to run the actual data collection. And we also need a lot of storage space for the data that we are generating. Each screening set on our glaciers generates 10 to 50 gigabytes of data, and a full data set can be upward of 2 terabytes. The need for storage is something that's often overlooked, and it could be a major endeavor for an IT department. So where is all of this data coming from? One thing to remember is that for imaging is quite complex, and for each final high-resolution image, there are at least 4 steps. The first step is the generation of a low magnification atlas. Then we select a low atlas. Then we select a low magnification square. We identify all the different holes. Then we take a medium picture of the holes into which we select a focus target and then the areas that we want to actually image. And then we collect the full high magnification image. This procedure applies to when we do screening and when we do data collection. And a full Cryo-EM experiment involves both screening and a screening step and a data collection step. The screening step is necessary because, as I mentioned before, vitrification is not simple or reproducible. And there are many, many variables that need to be tested to get a good grid. So for one data collection, we end up needing to prepare and screen many grids. And I think it's useful to spend a couple of minutes on the screening process itself to really understand what we are looking for. We screen grids to evaluate characteristics that will indicate if a grade is suitable for high-resolution data collection. One thing to keep in mind is that none of this information that we extract from the screening process can say anything regarding sample integrity or issues like preferred orientation. That is something that will pop up or will be evaluated during or after a full data collection. The first step is usually taking an atlas of the grade. And from the atlas that we use to identify how much imaging area is available. And for the atlas, we select 2 to 4 square magnification images, usually selecting them in areas of the atlas that appear to be of different ice thickness. For example, we usually target an area that has a thick ice, an area that has medium or medium to thin, and an area that has a thin ice, visually from the atlas. For each square, we collect 1 or 2 whole mags images, and then we select 4 targets. Targeting may be, in a couple of cases, the middle of the hole, in other, the side of the hole. The final images that we collect will provide information as to the real ice thickness, the particle distribution, the particle aggregation, if particles like to stay on thick or thin ice, if they like the middle of the hole versus the side of the hole. In this set, for example, the ice was very thin and the particles tend to aggregate. In the second example, the ice is a little bit thicker, but the particles look much better and we can actually identify individual particles. But we also see that holes that we pick that are too close to the edge of the grid have crystalline ice, and that some of them have some debris or some dirt on them. Screening takes about 30 to 40 minutes per grid. So for a cassette with 12 grids, it's about a 4 to 6 hour job. The information we learn, in this case, for example, that the particles like medium to thick ice and that we should stay away from the edges of the squares when targeting, will guide the data collection setup. I want to spend a couple of slides on the concept of imaging area. A typical data collection materials produce, let's say, around 8,000 images. If, for the sake of the example, we do 1 shot per hole, we need 8,000 holes. With a 300 mesh grid, each square has about 900 holes, of which maybe half of them will be available for a variety of reasons. That means that we need about 25 to 30 squares to make sure that we can go through the entire day or night of data collection. During screening, we need to make sure that we have at least that many squares available for data collection. And there are other considerations. For example, the fact that the configuration of many instruments does not allow for imaging of the squares on the very edge of the grid. And so, for example, not all the squares that are visible on a glacial atlas can be used to set up our data collection on the Cryos. So this atlas looks okay, more or less. There are definitely a lot of border 30 squares in here. This one definitely looks not okay. But what about this two? Well, we can have probably 30 grids with 30 square. We can have a little bit more, a little bit less. One thing to remember is that not all the squares are the same. And so we can have a really good looking one that gives us a lot of images, but many others that can be less useful. For example, they can be cracked, and then we lose all the core of the grid. They can be dirty, as we saw before, or they can be small or have too thick ice. In general, these squares will provide less holes than we will need. And so, in order to be sure that we can go through the entire data collection, we will end up needing to set up more squares for the plus to be on the safe side and not run out of targets halfway to the data collection itself. So how do we set up a data collection? Again, once we have a suitable grid, we take an atlas. We manually select what we think are suitable squares based on what we learned during screening. At this point, this is manual. We set up the squares selected manually, but at this point, the process becomes completely software driven. And it could be slightly different depending on how the software is used. But in general, the next step for each square, the eccentric height is calculated, and then all suitable hole mags are identified. This list is queued for data collection. For each hole mag, the software marks the holes as possible targets based on a set of predefined parameters, ice thickness, for example, distance from the edges, etc. A focus target is also set, and it will be collected every so many images that we also define. This defines the imaging queue that is then set to the microscope, and then for each target in the queue, the microscope will collect an image that then collected and stored. Setting up a data collection, including all the necessary microscope alignments, takes about half an hour on the glaciers and might take over 2 hours on the Cryos. And then the data collection can run as long as we have targets for it. And with that, we have our beautiful data set. And the next time, in about a month, I will talk about data processing, what we actually do with this beautiful data and how we extract information from it. And for now, I would just like to thank you for your attention, and I will take any questions.
Giovanna, I want to thank you for an excellent talk. So we are now going to go into the live Q&A portion of the webinar. So if you have any questions, you'll see a Q&A button in your toolbar. You can go ahead and type them there and we will answer them live. So the first question we have is from Sean. So Sean asks, if a sample behaves well in a negative stain experiment, does that suggest it will behave well for the full Cryo-EM dataset collection?
Unfortunately not. A sample can be really good in a negative staining, and that is a very useful information to have, as for the quality of the sample, the integrity of the sample, the nice distribution of the sample. Moving from negative staining to Cryo-EM data collection, there is this one step, which is the vitrification itself, in which a lot of things can go wrong, and we will touch upon them on webinar number 3. And so the fact that the sample is well behaved on negative staining doesn't mean that it will be well behaved in Cryo-EM. It is important to know for us, though, that the sample is well behaved in negative staining, because that means that the sample is good. And so if we get a grade that is not ideal, for a cryo grade that's bad because there is aggregation, because there is ice, anything that can go wrong, then we know that it's our vitrification process that needs to be refined and not the sample. And so it's up on the microscopist at this point to test many different cases, to screen very different conditions to find the optimal condition for that sample.
Sure. So following up on that, Giovanna, do you mind touching on, are there ever times where somebody might only want to do negative stain and that would be sufficient or even preferable?
Yes. So for samples that are, for example, very flexible, and all we want to see is maybe a distribution of conformations. I always speak of integrins as a good example because they are good examples. They are very interesting molecules. They are very, very, very flexible. And in solution, they have many different conformations. And sometimes what we are interested in is just the distribution of those conformations. How many have the leg closed? How many have the legs spread apart? How many are in different orientation? Or we want to see the effect of a ligand or a Fab that we bound to the integrins. In that case, negative staining is enough to do the analysis that we want to do. It's also enough if we just want to have a very rapid envelope or low resolution information, for example, to make sure that our complex is formed, or have a very not residue by residue level, but like peptide level information or envelope level of a Fab binding to an antigen, for example. So there are cases in which negative staining can be useful, and it's faster and cheaper. So it's something that should always be considered.
Thank you. We have another question. What do you do when the sample likes carbon more than ice?
So either you change the substrate. So instead of using carbon, you're using gold. And then maybe that can drive the sample onto the holes and in ice rather than stick to the surface. Or you just go with the flow and use a continuous carbon grid, for example. If the sample is big enough, even the very thin layer of carbon that we add, it's not going to be enough to disrupt the signal to noise ratio, for example. And so we can just take advantage of that fact and use that. But usually the first thing we do is try to change the substrate or the grid type.
So similarly, a question about grid type. So Evelyn asks, how do you choose what type of grid material, copper, gold, nickel, is optimal for your protein?
Well, it's very empirical, especially if that's the very first time that we try to vitrify a sample. We really don't know anything about it. And that's why the first step on our screening protocols usually involve trying slightly different concentration, 1x, 2x, 5x of the sample, and different grid types. And then based on what we see on the first round of screening, we decide, okay, if we like better gold grids. And then maybe we try different gold grids at that point. Gold on gold, carbon on gold, or different size holes or something like that. But upfront, it's basically an experiment. Try what works best.
So Arjit asked, can sample orientation bias be resolved via sample preparation techniques? How is stage tilting helping the situation, or how can it help the situation?
So we will talk more extensively about these cases. This case, like many other problems that we observe during the third webinar, but yes, vitrification condition, as long as we try to alter the air-water interface, which is what causes the preferred orientation, for example. And we can do that using different detergents or using different additives or using a different vitrification system. We can definitely ameliorate, if not completely solve, the preferred orientation. We do use tilted data collection, and that comes into play very often when we tried all the little tricks at grid preparation level. We found a condition that maybe improves the distribution of views, but is not optimal. And then we will take that condition and we will put it on a tilted data collection. And between the two, we usually manage to get a data set that we can use to solve a structure.
We have a question from Valeria. Can one use Cryo-EM to capture phase transition liquid droplets / temperature dependent liquid to solid hydrogels?
I am not sure. I don't think so. I never tried. We are freezing the sample. And so if that's something that you offer with, you can observe under maybe a gradual change in temperature, then we cannot do it. Because we go from room temperature to liquid nitrogen temperature in milliseconds. And there is no way that we can visualize anything that is transient in that span of time.
Thank you. We have a question from April, again about negative stain. So if the sample looks high concentration and negative stain, but you see less particles resolved on a Cryo-EM grid, what could be the cause of this?
Oh, maybe a lot of the particles get stuck to the air-water interface, and so you don't see them in solution in the level at which we focus, which is awfully in between in the middle section of the ice that we are looking at. It might be that they like to stick to carbon, and that's why we have a lot in negative staining, because they adhere to the carbon support, and so they are not in the holes anymore, but they are adding to the carbon. This just to come to mind. It might be that I guess those two. There might be other reasons that I can't think about now, but mostly I think it has to do with the interaction of the particles with the ice, with the water, with the ice, and with the substrate.
Sure. So as a follow-up, do you mind touching on when you say air-water interface, what does that mean, or what kind of effect can it have on the particles?
So very, very simply speaking, the air-water interface is the interface between the very thin layer of water. When we prepare the grids, we put a solution on the grid, and then we block the amount of the excess of solution away. What's left before vitrification is a thin layer of liquid with the particles in it. Now, the surface between the liquid and the air, it's big at that point. There is the ratio of air to liquid, there's a lot of air and very little liquid. Particles tend to adhere, to stick to this air-water interface. And they are hydrophobic, they are attracted, they are hydrophilic, they are attracted by the surface. They may form, they may denature, that's one of the biggest consequences. They may just form a layer of particles all oriented in the same direction, and that's the cause of the preferred orientation, for example. There are other things that can happen. What we try to do with detergent, for example, is to disrupt this air-water interface, basically putting a layer of detergent in between so that the particles don't get in contact with the air in those millisecond to seconds that it takes to vitrify the grid. I hope that answered the question.
Yeah, I want to mention the air-water interface is a hot topic for Cryo-EM. So for anyone who's interested in learning more, we do have a blog on our website that goes into this topic a little bit more in depth. And some of the next couple of questions are going back to grid types. So we have a question from Vikash. Does the ultrafoil holy gold film grid produce better data on a Krios? And is it any different? Is there a different data collection strategy on a Krios?
So one thing I learned is that grids don't make a good data collection. It's the sample that makes a good data collection. So you can optimize your grid choice based on your sample type. And if your sample type behaves well on ultrafoil gold holy grids, then yes, you will get a much better data set compared to your sample on carbon grids. But a priori, you cannot say that. And it's actually very difficult to say, oh, my sample will definitely do better on gold, because that's not true. And as it's true that it's not possible to say gold grids are always better than carbon, because again, it depends on samples. And we had a lot of samples that were perfectly fine on carbon and really badly behaved on gold, and vice versa. And so it is the sample that defines the quality of the data collection. Data collection strategy on the Krios, there are many. You can go as fast and as slow as you want. For example, you can do a single shot per hole. You can do multiple shots per holes. You can tilt the data collection. Again, it depends on what you're looking at and what your needs are. You may want to collect a lot of images. You may want to collect fewer images, but of very high quality, and then the targeting will be much more accurate. Or if you just, you have a lot of time, you just collect whatever you can. And that's another way you can do the data collection.
Yeah, we do wish there was one grid type for that worked for everything.
For everything.
If only.
If only.
Yeah, we have a question about hexagonal grids. So could you comment on the hexagonal grids and how they're integrated within the software, and how many shots you can take per hole?
Yeah, the XO foil, right? So you take one shot per hole, and thank you, because the holes are very tiny in this grid, much smaller than normal holes that we use. And so it's one shot per hole. The advantage is that a whole mag view, you have a lot of holes. And so you can select a lot of targets for one single focus point, for example. And that's why it allows you to go much faster. The data collection is basically the same. I think there are some parameters that need to be adjusted a little bit to take care of the fact that the holes are small and they're close to each other. So the beam needs to be very tiny, very small, much smaller than a standard data collection in diameter. Otherwise, you hit one hole and you also manage to irradiate or to clip all the holes surrounding it. And then the point of having a lot of possible targets is lost at this point. So these grids work well when you have an FFI system installed, for example, because then you can also use maybe slightly larger beam size and avoiding the problem at the edge of the beam.
Thank you. And then we have a couple questions related to specific sample types and considerations for those sample types. So Isaac is asking, what type of grids are recommended for DNA binding complexes for Cryo-EM using DNA and the protein on the grid?
It depends on your protein. And so we will start with carbon, gold, maybe nickel, titanium, and we'll see which one works better. Again, there is really no recommendation. There might be trends. So some samples work better in some grid types, but it's really hard to say it up front, and it's much safer if you always try at least 2, 3 different things at the beginning, and then select the optimal grid for the sample.
Thank you. Another sample specific question. So Carla asked, does the workflow you presented apply well to ion channels?
That's the one I present is a general workflow. The applies to anything, membrane protein complexes, small protein, big proteins. The difference in how you get to the grids. And so there might be tricks or things that you have to be very careful with or about when you work with membrane protein compared to soluble proteins. But once the grid is prepared and it's good, and we know it's good, then the workflow for data collection doesn't change.
Thank you. Another question about sample types. So Samia asked, what challenges arise in trying to image when there are hydrophobic molecules that are part of the example or part of the sample, giving the example of an antibody which is bound to lipids?
The lipids, individual lipids, or a chain of lipids or membranes. So again, hydrophobic molecules, we can visualize detergent micelles in which membrane proteins are embedded. So the way we treat them is there are no differences, I would say. The problem in this specific question depends on the size of what you're looking at, because a fab by itself is on the very small size for cryo-EM. And if the lipid that is attached to the fab, it's a fatty acid, then it becomes impossible, but not because it's difficult to prepare the grids, because of the nature of the sample. It becomes very difficult because it's hard to collect data and hard to pick the particles and hard to interpret the data because of the size of the sample itself.
Sure. Do you mind sharing a quick refresher on the size limitations for cryo-EM or considerations?
Yes. So we need to be able to see the particles on the images, basically. And that we need to be able to see the particle, not us, but the software that does the data processing. And so we need to be able to see the particles, pick the particle, isolate them, and then, as we will see next time, make a 2D classification and a 3D classification, which means we need to align them and orient them, both in a 2D dimension, in a B-dimensional and 3-dimensional. If a particle is too small, we can do that because we won't be able to see them. And then even if we see them and we extract them, if we don't have points that allow us to orient the particle, then the 2D classification or the 3D classification is not feasible. For experience, we learned that samples that are at least 80 kilodalton on ordered mass, so there's really 80 kilodalton that we will see, and up, anything up, is suitable for cryo-EM. Samples that are between 40 and 80 kilodalton can be worked on. It takes a long time. It takes a lot of prep time, a lot of analysis time. But 80, I would say 80 is the minimum size.
Thank you. We are coming up on almost the end of our time, so we have 2 more questions. So we have a question from Frank. If the sample contains very high HSA concentration in the matrix, removal will result in too much sample loss. So what would be a reasonable strategy for performing EM?
Then you switch to the HSA with something that stabilizes your complex, high salt, I don't know, something that is not so carbon rich or it doesn't absorb so many electrons. So the problem of having adjuvants like HSA or sucrose or a high level of glycerol or that kind of stuff is that they generate a very high background. And it makes visualizing the particle of interest much more difficult than normal. And so if the sample requires HSA for stability, one thing that could be done is to keep it at the concentration required up to the very moment in which we vitrify. We dilute it down immediately before vitrification, and then we hope that the dilution is enough to remove enough HSA that not to have background in it, or try to find ways to stabilize the complex or the protein that does not involve this adjuvant or similar adjuvants.
Thank you. All right, so our last question for this live Q&A. So it's again about negative stain. So are there any advantages to using negative stain over cryo-EM for studying PROTACs specifically?
So it will give you a lot of information about flexibility of these complexes, which are very flexible. The problem with negative staining and PROTACs is that negative staining works at nanomolar concentrations. And we use, nanomolar concentration. And at those concentrations, these samples tend to fall apart a lot. And what we have learned over the past few years is that, especially with PROTACs or molecular glues or all those things, you need to keep the protein as the concentration of the sample as high as possible to avoid falling apart. And so, yes, negative staining will give you a lot of information, but at the same time, it will basically destroy your sample. So it's not really amenable for that kind of analysis.
Okay, thank you. All right, with that, we are going to conclude our first webinar from our Cryo-EM Back to Basics series. So I want to give another big thank you to Giovanna for an excellent talk and for answering all the questions. And a big thank you to everyone who attended and contributed questions. So if you have any questions that you think of or you want to get in touch with us, you can feel free to email us at info@nanoimagingservices.com. And I also want to remind everyone that if you registered for today's talk, you will be receiving a recording. Our next session will be February 27th. And for that session, we'll be covering topics of data processing and interpretation. And so with that, we will say goodbye. Thank you all again, and hopefully we will see you all next month.
Thank you.